So we have proved up to this 4 raised to n is less than or equal to 2n raised to 1 plus root n. The product primes between root n and 2 by 3n and primes between n and 2n. Okay, so now we are close to the proof. So assume that there is no prime p with n less than p less than or equal to 2n, right? We assume the contrary. So what happens? So the second product in hash, so hash is given like this. So this is the second product. Suppose there is no primes there, then that prime, the product is 1. Right? What we are left with only these two fellows, right? Because if there is no prime, then what about this? The first product here. We have proved in the initial step that the product of primes, prime less than or equal to some x, this is equal to 4 raised to x minus 1, right? So we can use that. So using that idea, we'll get 4 raised to 2 by 3 minus 1. And of course, I mean, this is not equality, this is less than or equal to. So then 4 raised to x minus 1 is always less than 4 raised to x, right? So we can write 2 by 3 n instead of 2 by 3 n minus 1. So we get this inequality. So finally we get 4 raised to 1 by 3 n, because this 2 by 3 will go here, or you multiply appropriately. You get 4 raised to 1 over 3 n less than or equal to 2n raised to 1 plus root 2n. Okay. Now this would be false for large n. So for that, observe this fact. When alpha greater than or equal to 2, alpha plus 1 is less than 2 raised to alpha. That's very easy. You give 2, then this will be 3. 2 raised to alpha is 4, 3 less than 4, and it goes on. So this is true for alpha greater than or equal to 2. If you want to prove in using induction, that's very easy. We assume it for alpha and we prove for alpha plus 1. So alpha plus 1 is less than 2 raised to alpha plus 1, right? Yeah, because we assume this is true for alpha, right? Now 1 is less than 2 raised to alpha, so this is can be written as 2 raised to alpha plus 2 raised to alpha, right? Then that is 2 times 2 raised to alpha, which is 2 raised to alpha plus 1. So alpha plus 1 is less than 2 raised to alpha plus 1. So that's true for that. So you take any alpha greater than or equal to 2, this inequality is true. Now, so we prove the induction. Now you look at 2n. You write 2n is equal to 6th root of 2n raised to 6. That's not very difficult, right? Yeah. Which is of course less than floor function of 6th root of 2n plus 1. Why? Because we already proved that this case, right? We have proved before, raised to 6. So using that, I can write that. Now what we can say, you assume this is a alpha, so alpha plus 1 is less than 2 raised to alpha, we have just proved. So use that idea. It's 2 raised to alpha, right? Okay, and the 6 is there, right? So 2 times 6 times floor of that. And since box x is less than or equal to x, you can replace that. So finally 2n less than or equal to 2 raised to 6 times roots 6th root of 2n. Okay, we get that. Now observe one more fact. If n greater than or equal to 50, then we prove that 18 is less than 2 times root 2n. That's not very difficult. Suppose n greater than or equal to 50, then 2n is greater than or equal to 100, then root 2n is greater than or equal to 10, right? Take both sides root. Then multiply both sides 2, then 2 times square root of root 2n greater than or equal to 20, which is of course greater than 18. So this inequality is true. 18 is less than 2 times root 2n. Okay, now now you start writing like this: 2 raised to 2n is equal to 4 raised to n, right? So 4 raised to n can be written as 4 raised to 1 by 3 n raised to 3, just a manipulation. And we already proved this fact, right? Here, just before this, 4 raised to 1 by 3 n less than 2n raised to 1 plus root n. We apply that here. Then you will get like this: 2n raised to 3 times 1 plus root 2n. Okay, so now what you can do, this 2n, you already did one more work here, right? 2n is less than or equal to this, so you replace 2n by this 2 raised to 6 times here. Okay, and this will same as here. Then when you manipulate, then you will get 2 power, this is equal to 2 power 6 root 2n. Multiply inside 18 plus 18 root 2n. Now 18 is less than 2 times root 2n, right? So you replace that here. So then you get it is less than of this. Then you take out then you add this, so you get 20 root 2n and 6 root 2n, right? Maybe you can write that here. 20 root 2n, okay, 2 power, okay, or 2 power. So that would be compressed to 2 raised to 20 times 2n raised to 2 by 3. So finally what you are getting, 2 raised to 2n less than 2 raised to 20 times 2n raised to 2 by 3. And y equal to 2 raised to x is an increasing function, right? So definitely, and it is a 1 also in that part. So you can if 2 raised to x is like this, if x less than y, if and only if 2 raised to x less than 2 raised to y. So definitely the exponents can be 2 raised to n is less than 20 times 2n raised to 2 by 3. From that, just 2n raised to 1 by 3 is less than 20, 2n less than 8000 by cubing both sides. Finally what you are getting, n less than 4000. So n greater than 450 and n less than 4000. That's what happens when there is no prime, there are no primes between n less than p less than or equal to 2n. But that is that's false, because n less than 4000 and whatever greater than 50, we have proved that the Bertrand's postulate is true. There is a prime between every n and 2n. So our assumption is false. Our assumption that there are no primes between n and 2n is false. So that's the proof. So thank you for your attention. So we will be doing many classical proofs like this. These proofs are it is long. Then we have to split into many parts so that you will be able to understand very easily. If I do it in one part, you will be sometimes bored. So any doubts you can ask through the comments, and you can ask some proofs whether you wanted to understand more through this channel. Thank you.